This is SpaceTime, Series 29, Episode 95, for broadcast on the 10th of August 2026. Coming up on SpaceTime, spectacular vortices discovered on the Sun's surface, the event horizon of merging black holes seen for the very first time, and Starship recovery efforts now underway off the Western Australian coastline. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have for the first time observed swirling whirlpool-like vortices deep inside the Sun's photosphere, its visible surface. The structures, called Kelvin-Helmholtz instabilities, which were detected on the edges of solar magnetic regions, are a major step forward in science's understanding of the dynamics and evolution of solar and stellar plasma. The findings, reported in the journal Nature, are based on data collected by the world's largest solar telescope, the National Science Foundation's Daniel K. Inouye Solar Telescope on the Hawaiian island of Maui. The new time-lapse video and images reveal a solar landscape unlike anything ever seen before, and it's allowed the first ever confirmation of Kelvin-Helmholtz instabilities, a phenomenon that's long been predicted by theory but couldn't be proven until now. Kelvin-Helmholtz instabilities are an effect caused by fluid motion. It occurs when two fluids slide past each other at different velocities, creating a sort of shear effect at the interface, causing small disturbances to grow into striking wave-like or spiraling vortices, looking like breaking ocean waves. Since its original formulation by Lord Kelvin, Hermann von Helmholtz, around 1870, Kelvin-Helmholtz instabilities have been observed and investigated across many areas of physics, including fluid dynamics, meteorology, oceanography, heliophysics, and astrophysics. The instabilities observed at a variety of scales, from small lake and ocean waves in windy conditions to cloud formations on Earth, to the atmosphere of gas giants like Saturn and Jupiter, and the interaction of the solar wind, the constant stream of charged particles flowing out from the Sun, with planetary magnetospheres within our own solar system. One of the study's authors, the Deputy Director of the National Solar Observatory, David Bobholz, says the discovery of Kelvin-Helmholtz instability in the solar photosphere, backed up by numerical computer simulation analysis, represents a major scientific breakthrough. The swirling vortices of magnetic solar plasma have become an area of increased interest for solar physicists. They could be an effective source of free magnetic energy which powers major solar activity, including explosive events from tiny nanoflares to massive solar flares, jets and coronal mass ejections. And of course, these are the main contributors to space weather, which can severely disrupt our modern technological infrastructure, including power grids, satellites, GPS navigation systems and global communications. The leading theory on how the Sun builds up magnetic energy is known as flux braiding. As magnetic field lines twist around each other like braiding hair, they create a tense, unstable setup. When that tension gets rapidly released, the tangled magnetic field lines snap across each other and then reconnect in new shapes through magnetic reconnection. And this sudden rearrangement releases a massive burst of energy as the system settles back down into a calmer, lower energy state. What scientists don't fully understand yet is what causes the magnetic twisting and braiding to happen in the first place. And that's where this new discovery comes in. Those small swirling patterns from the Kelvin-Helmholtz instability might be the answer, or at least part of it. Since the swirls seem to be happening consistently and everywhere on the Sun's surface with a magnetic field strong enough, they could be the everyday engine that keeps twisting the magnetic field lines and consequently setting the whole process in motion. So the authors analysed and compared the high-resolution Inouye observations with computer simulations of the solar photosphere created using highly specialised codes. These computer simulations are built using some basic physics equations that describe what's happening in the Sun's atmosphere, and they're an important tool in the interpretation of scientific data, allowing astronomers to see things that are hard or even impossible to measure directly by observation, thereby giving them a real insight into processes that would otherwise be hidden. And the authors found literally dozens of vortex-like structures along the edges of magnetic areas, both in the observations and in the simulations, which were both strikingly similar in characteristics and dynamics. For example, the average space distance between vortices, known as the instability wavelength, ranged from between 50 and 65 kilometres in both cases. The study shows that our Sun's consistently bubbling surface, or granulation, interacts with magnetic structures to create areas where neighbouring layers move at different speeds, providing the conditions necessary to trigger Kelvin-Helmholtz instability. The National Solar Observatory's chief technologist, Thomas Ramil, says Kelvin-Helmholtz instability is a likely mechanism that contributes to the heating of the Sun's outer atmosphere, the corona, which is millions of degrees hotter than the Sun's surface. And that's been one of the biggest mysteries in solar physics. After all, things are supposed to get cooler the further away you are from the heat source. The data also shows that the swirling effect efficiently mixes magnetized and non-magnetized plasma on the Sun's surface, thereby enhancing the diffusion of magnetic fields throughout the solar atmosphere. The diffusion resulting from Kelvin-Helmholtz instability is a key factor scientists use when building models to predict how magnetic activity changes over time, not just for our Sun, but for other stars as well. The Sun's magnetic field is generated by a dynamo process, which acts sort of like giant cosmic engines, turning the star's rotational energy into magnetic fields. However, because the solar magnetic cycle is only 11 years long, a remarkably rapid timescale in cosmic terms, the generated magnetic flux must dissipate efficiently, and current models struggle to explain this rapid diffusion. And that's where Kelvin-Helmholtz instabilities come in. They could act as a key source for this missing magnetic diffusion. This is SpaceTime. Still to come, the event horizon of merging black holes seen for the first time, and Starship recovery efforts now underway off the Western Australian coast. All that and more still to come on SpaceTime. Astronomers have for the first time detected gravitational waves from the event horizon during the actual merger of two black holes. The observations, reported in the journal Nature, are opening a new window into one of the most fascinating and least understood processes in science. It's where quantum physics and theories of general relativity intersect. A black hole is a point of infinite density in zero volume, a singularity. They're called black holes because nothing, not even light, can escape its pull if it gets too close. That's because the escape velocity from a black hole is greater than the speed of light, and the event horizon is that point of no return surrounding a black hole beyond which matter and energy can no longer escape the singularity's gravitational pull, disappearing forever from our universe. They say in space no one can hear you scream, but it seems that you really can hear the sound of a crash when two black holes collide. Using the loudest gravitational waves ever heard, scientists have for the first time been able to witness the previously elusive event horizon at the actual moment of collision, right before all the light, sound and matter are swallowed for eternity by the newly formed black hole. The authors measured this last sound, a gravitational wave, which the black holes made when they crashed. Hidden within that signal is a small component called direct waves, which had not previously been well understood. And this allowed the authors to measure two fundamental black hole properties from close to the event horizon: rotational frequency and surface gravity. The scientists studied the gravitational wave signal coming from an event called GW250114, which was recorded last year by the LIGO Laser Interferometer Gravitational Wave Observatories in Louisiana and Washington State. The GW250114 black hole merger was the loudest binary black hole signal ever observed, and some 3 times louder than the first gravitational wave signal detected over a decade ago. One of the study's authors, Professor Robert Ward from the Australian National University, says these measurements mark a first step towards future tests of general relativity using direct waves. It means astrophysicists will be able to study the strength of extreme gravity at the black hole's event horizon, as well as phenomena like frame dragging, where black holes quite literally are dragging the very fabric of space and time, in the process creating an environment where nothing is able to remain stationary, relative to a distant observer.
When two black holes are merging, they start off far away from each other, and so they gradually spiral into each other, getting closer and closer. And then at some final point, they crash into each other, and they make a heavier black hole at the end of this. And this is what we see with gravitational waves, which we first saw just over 10 years ago. And we've been able to view this process, and we've seen hundreds and hundreds of black holes doing this now.
The merger of black holes and gravitational waves is fascinating. Sounds like a chirp, just increasing in frequency in gravitational waves at least.
Sounds exactly like a bird chirp.
Exactly. That is because the two black holes getting closer to each other, so they move faster. And when they move faster, the wave carries higher frequency. So that's why you hear, or like when we see the waveform, the frequency gets higher when they get closer and eventually merge.
And you saw another wave within that structure.
What we did is we decoded a piece of the signal, which was inside these observations that we've been making, that no one was previously able to interpret. And we've brought in a new way to be able to clean out all the other stuff, which is hiding this piece of the signal. And so then we can isolate this part of the signal, which is very interesting, which tells us a lot about the physics near the black hole horizon and allows us to test what's going on in this region of space.
And this was the direct waves.
Yeah, exactly right.
And what does that tell you?
Oh, that is very interesting. Black hole event horizon, that is usually referred as a point of no return. Nothing can escape, not even light. But this direct wave component actually brings us some imprints the remnant black hole horizon leaves in the gravitational wave signal. That actually allow us to test the black hole horizon, its frequency and surface gravity. In other words, like how fast the horizon is spinning and how strong the gravity is near the black hole horizon. That is the key information we can decode out of this direct wave component.
And what does that tell you about the physics of the merger itself? Are the event horizons moving in the same direction? Is the black hole spinning is the singularity spinning in the same direction? Or are they in opposite directions? Or can they be in any way at all? Is there some sort of synchronicity going on just prior to the merger?
This tells us a lot about the remnant black hole. So the black hole which is formed at the end of everything. And this is also why this direct wave is so powerful, because you're right, before the merger, there's all of this complicated physics going on. Are they spinning in the same direction? How heavy are they, one compared to the other, etc.? There's a lot of different parameters, whereas this direct wave is actually extremely simple in the sense of it only depends on these two very simple properties. And so this is also what makes the direct wave so interesting, in that it reveals a lot of insight into the remnant black hole's horizon physics.
Also kind of interesting because when the final black hole is formed, it's highly spinning, right? Because the two black holes form one and it's spinning really fast. It drags the space-time around it. So we call it a frame dragging. Then kind of it removes some of the history, like complicated history before the black hole merged. And when it gets to the final stage, it sort of just gets dragged by the final black hole. And that's why the direct wave piece is so clean and just to carry the information of the final black hole.
Will this help with studies of topology in black holes and trying to understand Hawking radiation?
Ooh, that's a very interesting question. I think this is the start of being able to analyze and study, like you said, topology and the space-time physics with this part of the signal. We hope eventually it may provide insights into all of that, but that's still we're still just opening this door to trying to understand how to use it. So we can't give a conclusive answer yet about what insights it may bring in the future.
I think lots of work still need to be done to better understand this kind of information and maybe possibly open some new avenues to study black hole horizon physics and like fundamental physics or
general relativity, Hawking radiation. Yep.
We know very little about black holes other than their mass and their rotation. What can we still learn from them?
So one thing I guess is at the end of the day, black holes are remarkably simple objects. Like you said, they only have their mass, their rotational frequency, and theoretically they could have charge, but for any real black hole, it's extremely unlikely they have charge. So even though we know you say we know relatively little about it, that's because there's not that much to understand about the black hole itself. But then we're also incredibly interested in probing the physics just outside the black hole, the physics near the horizon. And this is where a lot of the interesting things like Hawking radiation happen, where you have the interaction between general relativity and quantum mechanics. And so probing this region just outside the black hole horizon is what we hope to be able to contribute something to with this direct wave signal.
Now, this particular black hole merger you were looking at, GW 250114, how far away was it? What do we know about its location in space? And
I think it's about 400 megaparsecond away from us. Roughly 1.3 billion light years.
Do we know about the mass of the progenitor black holes?
Yeah, so they are formed by approximately 2 black holes, which were each about 30 solar masses, 30 times the mass of the sun. And one interesting thing about GW 250114 is it's a remarkably standard system. That's to say, we have seen lots of other systems with very similar properties, similar initial masses, similar initial spins, mass ratios, etc. But the uniquely interesting thing about GW 250114 is that it is relatively closer, and so we can see this extremely loudly, and so we are able to use this to do lots of tests of physics.
Remarkably loudness of the signal is because we have our detector way better than 10 years ago. There is a lot of work getting into upgrading these extremely sensitive detectors over these 10 years. So almost a similar signal as 10 years ago actually give us a much, much cleaner signal in our detector, and we are able to carry out these detailed studies.
Of course, one of the big problems about gravitational wave detectors is that there aren't many of them. So working out exactly where an object is in space is still difficult. We've got the 2 in the United States on either side of the country. You've got 1 in Europe and 1 in Japan, and others are being built. But we were offered 1 in Australia at some stage, but the government of the day turned it down, which is very sad. But we need more gravitational wave detectors to get a better picture of what's happening in space.
Yeah, for sure. And actually, group of people in Australia working really hard to propose a gravitational wave detector in the future in Australia, and a much better one for better study in getting deeper into the universe.
This is OzGrav?
OzGrav, including everyone working in OzGrav and the bigger community.
Oh, fingers crossed with that. How advanced are those proposals?
I guess that's still at an early stage because, internationally, there are proposals for the next generation gravitational wave detectors. They will be way more sensitive than what we have right now. And there are proposals in the US, in Europe, and in other countries as well. And Australia is also working on the proposal and looking into pathways to get to future better and more sensitive gravitational wave detectors, which can bring us more fascinating science.
So that would maybe allow us not just to observe in gravitational waves black holes and neutron star mergers and things like that, but maybe even the merger of supermassive black holes? Is that what we're talking about?
That will be a different frequency range. That will be something we can observe with future space-based gravitational wave detectors.
That's LISA, right?
And actually, in terms of supermassive black hole, there's another way to study them, which is already happening with a set of pulsars, which is called pulsar timing array. They are using these pulsars, the astrophysical object, as like a telescope in the sky to study the background of supermassive black holes.
So when the pulsar signals get out askew, then you know there's a black hole supermassive black hole merger going on.
Yeah, this is like a pulsar have really good timing, and their signal arrive on Earth should be super accurate. But if the space-time is sort of changed by the passing by gravitational wave background, then the pulsar signals arrived. The time of those pulsar signals will be slightly changed depending on which direction it comes from. So we can use that kind of information to infer the space-time geometry in the universe.
That's Professor Robert Ward from the Australian National University. And this is Space Time. Still to come, SpaceX Starship recovery efforts now underway off the Western Australian coast, and later in the Science Report, reshaping science's understanding of the evolution of mammals during the age of dinosaurs. All that and more still to come on Space Time. SpaceX are towing their Test 13 Starship prototype back to shore after it survived its Indian Ocean splashdown off the Western Australian coast. While other test flights have succeeded in achieving a soft landing in the sea, Ship 40, as the spacecraft's known, is the first not to explode and sink. To be honest, SpaceX weren't expecting to recover Ship 40. The Starship had just completed a successful test flight, launching on its Super Heavy rocket booster from SpaceX's Starbase on the Texas Gulf Coast, completing a textbook stage separation and then ascent to its planned suborbital altitude. Once in space, it successfully deployed 20 Starlink Type 3 satellites, the new ones which are now being released. It also undertook a test restart of one of its Surface Raptor engines, and that was followed by a flawless atmospheric re-entry to Saturn landing. Now, usually the heat of re-entry, the impact of the splashdown, and the remaining fuel inside the spaceship combined to trigger an explosion, resulting in the Starship breaking up and sinking. But this time, for the first time, Starship simply tumbled over into the water and floated, bobbing up and down. And that's provided SpaceX with an unexpected opportunity. The SpaceX recovery ship Go Australis monitored the splashdown from a safe distance and has remained nearby while mission managers were working out how to recover the spacecraft. SpaceX boss Elon Musk says a pair of Norwegian tugboats named Normand Ranger and Skimmer Tide were then contracted to carry out a recovery effort. The latest satellite images show what looks like a tow line attached to the Starship, and ship tracking data from marine traffic shows the two tugs moving at about 1 nautical mile per hour and broadcasting the fact that they had a restricted level of manoeuvrability, inferring that they were towing something. The recovery of Starship will provide SpaceX with a treasure trove of invaluable data about the test which they weren't expecting to get. Previously, they've always had to rely on visual images and onboard sensors during what were sacrificial missions. So to actually have a complete spacecraft to study will greatly advance the test program. Musk says Starship Test Flight 13 was so promising that SpaceX might now attempt to catch Starship back on dry land after the next test flight, which is likely to take place later this month or early next. Meanwhile, NASA are monitoring the whole operation closely as both a version of Starship and Blue Origin's Blue Moon lander will be used to shuttle crews and supplies from lunar orbit down to the moon's surface and back again, with missions due to commence with Artemis 4 in 2028. To meet that deadline, Starship needs to be ready for next year's Artemis 3 mission. That's where a manned Orion capsule will dock with both Blue Origin's Blue Moon lunar lander and the HLS, or Human Landing System version of Starship, in low Earth orbit. The Artemis 3 crew will evaluate Orion's systems, propulsion and communications, as well as spacecraft interoperability through a series of rendezvous and docking demonstrations involving both Starship and Blue Moon. The Blue Origin vehicle, Blue Moon, will have the same crew module as the Blue Moon Mark II test vehicle, complete with a functioning life support system, thereby allowing the Artemis 3 crew to enter and evaluate its systems. However, its propulsion system will use storable propellants instead of cryogenic fuels. Meanwhile, SpaceX's Starship HLS is expected to be equipped with a docking mechanism, but not an operational life support system. So the crew will remain on board Orion rather than entering the vehicle. Currently, both lunar landers remain under development, and both are yet to complete NASA's human rating certification process, required before manned operations can take place. After all that's done, NASA will decide which lunar lander they'll use for the historic Artemis 4 mission, returning humans to the lunar surface. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Scientists have developed a new blood test to help look for signs of Alzheimer's. The new test works by detecting a protein called phosphorylated tau 217, which is a biomarker for a buildup of amyloid plaque in the brain. It's this sticky plaque which is thought to play a central role in Alzheimer's disease. The new test could provide results in as little as 18 minutes, detecting changes in the brain decades before symptoms develop. Australia's Therapeutic Goods Administration has already approved clinical trials of tau 217, which are expected to begin shortly. A new study has found that e-scooter riders are 3.5 times more likely than motorcyclists to suffer traumatic brain injuries. The findings, published in the journal Scientific Reports, are based on data from more than 15,000 British trauma patients. The authors say, unlike people on motorbikes, e-scooter riders rarely wear helmets. They're also more likely to damage their internal organs, but less likely to fracture bones than motorcycle riders or bicycle riders for that matter. Analysing more than 20,000 self-reported e-scooter incidents, the study also found women reported worse injuries, possibly because e-scooters appear to be designed more for male body proportions. A remarkably well-preserved fossil from Mongolia's Gobi Desert is reshaping science's understanding of mammal evolution during the age of dinosaurs. Based on their fossil teeth, the new species called Tamiacan balcacilli has been described in the journal Nature. It belongs to a group of extinct mammals known as xylistides, which were on a different branch of early mammal evolution compared to most modern-day placental mammals. Xylistides have been known from isolated teeth and fragmented fossils for nearly 40 years. Their distinctive teeth, which are more specialised for eating plants rather than sharp insect-eating teeth found in many Cretaceous mammals, led paleontologists to suggest that they represent an unknown group of hoofed mammals. And this newly discovered fossil further supports that view. Measuring between 6 and 7 inches from head to tail, Tamiacan had elongated hind limbs that gave it an almost rabbit-like appearance. Based on these findings, the authors have concluded that xylistides were not placental mammals or especially placental-like in appearance, but a subset of the Zolamdalistoid group. A new study has shown that wireless charging for drones could be achieved using lasers. Currently, drones run on batteries and have to land in order to be recharged. Now, researchers have designed a piece of tech like a solar cell and put it onto the wings of a drone. When they shot a laser beam at it, the technology converted the laser's energy into electricity, making the propeller spin. The authors used heat-blocking technology and airflow to keep the device cool, thereby overcoming heat buildup from the laser's energy. A report in the journal Matter and Light claims they'll have to address many more challenges before the wireless charging system can take flight. But the authors say this is the first step towards refueling aircraft with nothing but light. Well, as we've all seen in recent US Senate hearings, it is a fact that governments lie to the public. Politicians do it, bureaucrats do it, and of course the Fourth Estate does it. So it's easy to understand why people would be sceptical about the stuff governments tell you. And sadly, this has given the true blue conspiracy theory Fruit Loops free rein to push their own beliefs. And one of the latest is that NASA's recent Artemis 2 mission, the first in over half a century to send humans around the moon, was all an elaborate fake. Now, it's been labelled a hoax by the same sort of mindset that claimed the original Apollo 11 lunar landing was faked, despite independent space agencies from a number of other countries photographing the landing site, as well as the return of regolith from the lunar surface at a time when robotic sample return missions weren't really a thing. Also, there's the ability for you to go out tonight with a laser beam and shine that beam on a retroreflector placed on the moon by human hands and receive a return signal 2.5 seconds later. Proof that humans walked on the moon. Or there's the simple fact that lots of other countries were involved in the mission, including Australia. And even after more than 50 years, no one involved in the program has denied the fact that it happened. And when you consider how governments leak and how people like to boast, that's pretty impressive. So, the takeaway is, you don't have to believe what governments tell you, but when a dozen different sources are all giving you the same advice, they may just be speaking the truth. Which brings us to an interesting survey of US residents conducted by the University of New Hampshire. It shows that 10% of respondents still think NASA faked the moon landings. So, as you can see, the collateral damage caused by dishonest government goes deep and affects many unintended areas. The skeptic's Tim Mendham says it also shows an appalling lack of basic scientific understanding. We're talking high school level stuff here. The sort of things that can't be faked.
We've sort of seen this before, don't we? Anything that comes out of NASA or anything that comes out of a scientific body, there's always some people who respond instantly saying it's a fake. Whether it's the moon landing or 50 years later, the Artemis 2 mission, people are instantly saying it's not true, they're not really in space, it's a deep fake sort of AI video. Honestly...
The question is why?
Yeah, why? I don't know. You look at it.
Is there some sort of a psychological problem these people have? Is it their need for relevance? I know secrets that you don't know, and I'm going to tell you what they are right now.
There's obviously a bit of that. I mean, people want to get notoriety, etc., and that's a pretty cynical motivation. There's nothing you can say to those people, quite frankly. Whether they're a flat earther, whether they're a Artemis 2 conspiracy theory, you can try and debunk their beliefs, and if they even accept that debunking, they'll jump onto another one. But once a conspiracy theorist, almost always a conspiracy theorist. And interestingly, interesting thing in this story, which I should add, is that the University of New Hampshire pointed out that 58 to 83% of people agreed with statements of basic scientific facts, such as the Earth is billions of years old or revolves around the sun. Now, that is worrisome. So 58 to 83 means, at the very best, 17% of people don't believe the Earth revolves around the sun or that the Earth is billions of years old, up to 42% of people who don't believe that thing. You think that's scientific literacy? That is as big a worry as anything, I think. The Artemis hoaxes are a very small minority. When you say 42% of people have trouble with the Earth being billions of years old or the Earth revolves around the sun, then you know you're in trouble.
I still get emails from flat earthers, so yeah, I'm not surprised.
I haven't had any for a while. I'm very disappointed. I have been invited to join the Illuminati twice.
Yeah, you're too busy with the Bilderberg group, aren't you?
That's right, Bilderberg, yeah. That's the one with the skull. That's skull and bones.
Look, I've never been to any of the meetings.
Your absence has been noted.
That's the Skeptic's Tim Mendham, and this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.